Welcome everyone. So this is our 59th live stream geometry, and we have two other people here with us, one from Vietnam and one from India. So this is number 59. So we've been doing it for quite a while, and if you'd like to join, feel free to email me at mgreenb801@gmail.com. It's in the description of my video. And the sessions are on Sundays at 8 a.m. US Central Time. All right, so I am going to share my screen. Today, we're going to be doing problems from the Saudi Arabia IMO training. So a lot of these problems, so they're all from the year 2021. A lot of them are taken from other countries' contests. So this problem right here, I think was from Buratino, who was from Vietnam, and he has a lot of really good problems. So this problem starts with a rectangle. All right, so we have a rectangle ABCD. All right, so this is point C. Whoops. Then we have point D. And P is on the segment AC. Whoops. All right, so that's P. Q, so then we want to draw the two circles, PAB and PAD. So let me make it, I think it might be better to make it like a taller rectangle instead of yeah, I think for this problem, I think it might be better to do it like this. So we have the circumcircle PAB and PAD. Let's draw those circles. And Q is on arc PB, so that QB is equal to QC. That's interesting. Okay, so then I think we want to use our perpendicular bisector tool. So that would be Q right there, and then we would also have point R. Okay, so this is Q. And then this is R. So I'm going to make it look better in just a second. And then CB. Okay, so then we draw the circumcircle of CQR. It's kind of interesting. And we want to see where it meets BC and BD. So it meets, or CB and CD. So this should be N. C. So that should be N, and this should be M. So I see we have two more people joining. So thank you both. Let me see if I can make M a little farther away. All right, let me move it around just a tiny bit. All right, so this is M. And we want to show BM equals DN. So let me hide some things. Hide that. I think that's really all I need to hide, actually. Oh, I need to hide CD. So BQC is isosceles and CRD is isosceles. I'll just draw on those segments just to make it. Oh, and you know what? I probably should draw C. Yeah, so I'm going to draw this, that. Maybe I'll draw this just so we can realize that that's like a circumcircle. Okay, so yeah, it's almost like a square, but I think it's okay. Actually, you know what? Yeah, I'll make it look more like a rectangle instead. There we go. So I see Vance just joined. So thank you for joining Con, Vance. So yeah, we're still on the first problem. So we want to show BM is equal to DN. We could use power of a point, because BM times BC is the power of B with respect to the circle. Maybe we could even use the power ratio lemma. But yeah, it's kind of hard to use the power ratio lemma. Let's see, is BMDN cyclic? No, I don't think so, because then it would have to be an isosceles trapezoid. I wonder if there's anything special about diagonal BD. So let me check that the problem's actually true. So if I calculate the length of BM, 3.56, and that's also 3.56. All right. See, how can I use power of a point? Should I draw the center of the circle? I wonder if that might help. Oops. It doesn't lie on the diagonal. Yeah, this problem's probably kind of hard because it was created by Buratino. Although it doesn't look like the configuration doesn't look that complicated. Do DR and BQ intersect on the diagonal? Let's see. If I draw DR, he likes rectangles and squares. Interesting. So we have Prem Joshi just joined. Oh, really? Like a really hard problem with squares? That's interesting. Yeah, send it to me later. Yeah, I really want to use the power ratio limit here. I just don't know how to do that. So, yeah, maybe we could find, are there any like congruent triangles we could find? Oh, really? Golden ratio problems? Interesting. Oh, yeah. You've seen like similar ones. What if, yeah, it almost looks like, okay, I don't think, what happens as I move P along the diagonal? It almost looks like, okay, yeah, you can see the tangents don't really concur. So if I move P, what happens to dn and bm? I wonder, is there like a degenerate case where we could solve this problem? Like as P approaches C, as P approaches C, those go to 0 basically. And then as P gets farther away, oh, we can't make too far away, P too far away because then points Q and R won't exist. But what if P is like the center of the rectangle? Would it be obvious in that case? Probably should be, right? Because then this would be like the circle with diameter CP. Okay, and so actually, I'm not sure if it's so obvious then. Let me see if we have any. It almost looks like these circles concur, although maybe that's just a coincidence. Yeah, that's really interesting. Let's see. Is that actually true? No, that was just a coincidence. Yeah, since it's a rectangle, I wonder if we could like rotate stuff. Let me check the chat. We have another person on. Thanks for joining. So yeah, maybe like I could rotate the figure because it's a rectangle. So often that helps. I'm just going to add in these points right here. So EF is parallel to A, B, and CD. And then I could also add these in. So yeah, like I'm thinking, what if we like rotated the figure? So what if I do this? So basically we want to show that BIND is a parallelogram. I don't know how much that really helps though, but we know that BIM is an isosceles right triangle. Yeah, I don't think that really helps much. Yeah, so for those of you that joined recently, we're still on our first problem. So we have a rectangle ABCD. P is any point on the diagonal. Then we draw the circumcircles PAB, PAB, and then, yeah, you can read it in the question, but yeah, BQC and DRC are isosceles. And then the circumcircle of CQR intersects the sides at M and N. And we want to show BM is equal to DM. I kind of like drawing these just because I want to use power of a point. So like if I draw this point right here, is there anything special about that that would let me use power of a point? I'm not sure. Yeah, I'm not sure. I don't know if those points would really help. What if I drew this point right here? Let's see. That is tricky. Yeah, if we don't use power of a point, is there another way to calculate dn and dm?
Maybe we can use equal triangles. Maybe.
Congruent triangles.
Yeah, congruent. Yeah, that's what I mean.
Okay. Yeah, what if we like translated the figure? Let's see, if bm were equal to dn, is there anything special we could do? Let's see. Maybe I could let dn meet the circle again. Yeah, what if I translated point P? Let me try something, because I feel like in a lot of these kind of rectangle problems, it's useful to construct a point P like this. Or I don't know, we could call this S, let's say. So APSB is a parallelogram. Does that help? Okay, so we want to show Bn is equal to Dn, but we know that Cs is equal to dP, and AP is equal to Bs. You know what, maybe it's better. Like, what if we reflect S across the perpendicular bisector of BC? So Oh, whoops, I need to do this one. Sorry. So then BS prime is equal to CS, which is equal to DP. And we want to show that DM is equal to DN. But those triangles don't look congruent. That's the thing. I want to try to get congruent triangles. Let me make sure that's. Whoops. Yeah. All right. I'm not sure what I'm doing here. Try to make a congruent triangle. What if I do this? No. Or maybe I can use Casey's theorem. What if I let me try something. Does PB pass through N prime? Let's see. It seems like a coincidence, but I'm not 100% sure. Okay, never mind. It doesn't work. All right, let's spend 10 more minutes on this and then we can move on to the next one. Maybe come back to it later. Actually, I never thought about doing the power of m with respect to this circle. Because I could do like mf times mb and nh times md. Delete that. All right, Sergio just joined. Thanks for joining, Sergio. So we're still on the first problem. It's a tricky one. Sorry for the noise in the background. So what if we reflect n over d? And then we want to show what if we, instead of doing that, what if we do this? I want to show BMID is a parallelogram. So basically, I want to show AI is equal to CM. So I could show AICM as a parallelogram. So basically, I wonder if these concur. No, that's just a coincidence. It's probably worth drawing the center of the rectangle.
I think we have RC equals RM.
RC is equal to RM or R?
RC is equal to RM.
Really? Hold on one sec. So I
think I miscalculate something.
okay.
Let me check.
Yeah, but maybe it's worth doing that too. Like we could make this into, so R is the circumcenter of this right triangle, and Q would be the circumcenter of that right triangle. So maybe let's try to do an angle trace. So we have this angle is equal to this angle, which is equal to angle RMN or RQN. Yeah, maybe we can find similar triangles. I wonder, is there any point where we could take like the trace of it? So like what happens as we move P around? So Q and R just go like up and down. So Q and R basically approach the midpoints. In fact, it even goes past it. So let me draw this point right here. I wonder. I'm just curious what happens to point I. Okay, it just moves along the diagonal. Are there any special points in this? If BM is equal to DN, then the center of the spiral similarity is the midpoint of arc BCD. Oh, of the circumcircle of the rectangle. So if we draw, okay. Let's draw that point. So that makes me wonder now. So these circles, are they tangent? No, it looks like they intersect again. But let's draw that midpoint. Maybe there's something special about it. So let's draw the perpendicular bisector of okay, so that's like where those two circles intersect. Yeah. And does it pass through? We draw the midpoint of AC. So yeah, it passes through the center of the rectangle. So if we move P around, so yeah, point J stays the same. That's kind of interesting because it says if we move point P, then point J stays the same. So is there something special about point J then? Because J is like independent of where we choose P. Is there some special ratio or something? So let me draw the other diagonal of the rectangle. So yeah, J is just the midpoint. Yeah, J is going to be the midpoint of that arc, like you said, BCD. So what we could do is we could define J to be the midpoint, and then we want to show that JCR, well, yeah, maybe it's a little tricky. All right, let's move on. Center of, basically there's a spiral similarity taking DN to BM. So it's the center of the similarity taking that segment to the other segment. So basically we would have DNJ is congruent to JMB. So JN should equal JM. So I think J is also the midpoint of arc MN. Yeah, so it's the midpoint of both arc MN and arc BCD. All right, I'm going to move on to the next problem, and we can get back to this later. But yeah, I think the others are probably a little bit easier. So here we have a triangle with orthocenter H, and we draw the three altitudes. So A, B, B, E, and
I have done this one.
Oh, you've done this before?
Yeah, the solution is quite easy too. So if you don't mind, I can save that, or you guys can just think about it.
Okay, you want to move on to the next one?
Maybe do you guys want to think about it? It's not really hard though. So
Okay. So yeah, we can do it really quick. See how quick we can figure it out.
Yeah. Okay.
So AD, BE, and CF. And H is the orthocenter. E, F is H. And DF intersects HB at M. Oh yeah, it does look a little familiar. I don't remember exactly. I think I might have done it too. So this is M. And this is N. And T is the circumcenter of HBC. So we know the circle of HBC, if you reflect it across BC, it's the circumcenter of ABC. So I think AD is equal to DG. Let me draw the center of that. Okay. So yeah, T, let me also draw the circle of ABC, and I'll call the center of it O. And I think, yeah, T and O are reflections across BC. So, and so are A and G. Okay, that was fast. So I'm just gonna type it all up really quickly. MN is the radical axis of the 9-point circle in HBC. So if we draw the 9-point circle, okay, so you're saying M and N lie on the radical axis of that. So because FM times MB is HM times MB. So yeah, so we have because these are cyclic. So FM times MB equals HB times BD. I think that's what it was, right? Or HM times MB. And we also have EN times NB equals HN times NC. So that means that M and N both lie on the radical axis of that circle. So MN is the radical axis of HBC and DEF. And so that means that so if we draw the 9-point center, call it S. So let S be the 9-point center of ABC. So that means that MN is perpendicular to ST. So basically, ST is perpendicular to MN. And then can we show AS and T are collinear? Is that just by reflecting? Because S is the midpoint of OH. And OT is equal to AH. So yeah, some of them, yeah, I don't know why this one's way easier. They're the same. I think they collected problems from a bunch of different countries, and some were easy and some were hard. But basically, T is the reflection of O over BC. So I think there's like, I think we need this step, right? So that implies that AH equals OT. And so that means AHTO is a parallelogram. So since S is the midpoint of OH, it's the midpoint of AT. So yeah. And then from there, we have AT is perpendicular to MN. I think we had to do this last step. I don't think there's any shortcut, but I don't know. All right, so I'm going to move on to the next one. This one actually looks kind of hard, so it's up to you guys. Or we could try to get the easy ones first and then do the hard ones in the end.
Yeah, let's do the hard ones in the end.
The hard ones in the end? Or did you say let's do the hard ones in the end?
Yeah, let's do them in the end. Let's just do the easier one first.
Yeah. So we have a triangle ABC. So it's inscribed in a circle O. Let's see who else is still on. All right. So let O be the center. Try to make it an acute triangle instead. We draw the tangent line at A. We want to see where it meets BC. And then let it meet at a point D. And H is the projection of A onto OD. It's the perpendicular. Okay, so this is H. And then we take the perpendicular from H to AB and AC. Kind of looks a little like maybe poles and polars, I'm not sure. So this will be E and F. And then EF cuts the circle at R and S. Actually, I'm not sure how easy this one is. It's hard to tell. Let me make this like an acute triangle. I think it might look nicer. So, and then move A like right here. So it cuts the circle at R and S. And we want to show that this circumcircle of HRS is tangent to OD. That's kind of interesting. This is a very interesting. I've never seen like a perpendicular from A to OD like this.
Is it not just a median line?
Oh, is AH just the symmedian? I think you might be right.
Yeah, you just reflect A over H and we got the tangent point.
Okay. So A prime, I'll call it, I don't like primes, I'll just call it something else, but AT is is this a median, basically?
Sorry, Michael, can you call the intersection of line RS and OD and draw the
Yeah.
RS and OD and you draw the circle of quadrilateral AEHF.
Yes.
I think we will prove that the lies on the radical axis of circle AEF and ABC, which means GI are convenient.
Okay, so like AI and G. Yeah. Okay, so we know G is on the radical axis. So is it? Let's see. So yeah, it looks like this circle. It's tangent. Because AH is a diameter. So this circle, it's tangent, and so like before we had that line, we know GH squared is GE times GF. And how do we know that's equal to the power of G with respect to the bigger circle? Oh, because BEFC is cyclic. Well, yeah, but G isn't on BC. Let's see. So RDO equals RSD. AO is the perpendicular bisector of RS. Is that true? Really? Oh, actually, so I know O is on the perpendicular bisector, but no, AO is not the perpendicular bisector of RS. Is G the midpoint of BH? Let's see. Yeah, it looks like it. And it looks like they might pass through this point. So this is kind of looking a little like the McKell point. That's a good observation. It looks like we could label this point. So yeah, it looks like G is this. Let me draw that again. So it's like G is the circumcenter of HJD, and it looks like AI and G are collinear. And so this, yeah, we know that's a right angle. So let's draw, so we want to show HRS as tangent to OD, and so it suffices to show angle RDO equals angle RSD. And that's the same as saying that triangles DGR and BSG are similar. So is GJ, yeah, tangent? I think GJ is tangent to the circle. Yeah. Well, yeah.
Can you redefine G? Because I think you connected too many lines, so I don't remember how we defined it.
How we define it? Yeah, I'm not sure how to. I guess we could start by defining it as the intersection of RS and OD, right?
Okay.
Is there a way then, how do we then show that GI and A are collinear? So we have GH squared is GE times GF.
So if we label G as the intersection of EF and OD, and if we could prove that GD equals GH, then G is the center of circle with diameter DH.
Yeah.
And a circle with diameter DH is orthogonal to O, because they are like D and H are like pole and polar, so DH must be orthogonal.
Yeah.
So if we prove that GD equals GH, we can show that G has the same power to O and AH.
Okay. So first you want to try to show G is the midpoint. All right.
Michael, I think you solve this.
Okay.
So, the quadrilateral ABTC is a harmonic quadrilateral, right?
Right.
So if we project it on the little circle, so HF. So JEH and F are harmonic, right?
Right.
So therefore, EF cut the tension at H. EF tension at H and the tension at J is collinear.
Okay.
It's a concur. It's concur. So GJ will be equal to GH.
Yes.
Yeah, and from that we could do the angle J to prove that G is the midpoint of DH.
Okay.
Okay.
All right.
After that, we need to prove G, I, and A is collinear, right?
Yeah. Yeah.
Which is similar to prove that J, I, H, and A is harmonic quadrilateral, right?
Yes.
Okay. So could you let we define I at as the circle AEF cut circle ABC, right?
Yes.
Yeah. So the angle AIH will be 90 degree, right? So
Yes.
yeah. So if you let AO cut the circle ABC at one point, IH in that point will be collinear.
Yes.
Yeah. Okay. So the thing is that we need the J, I, H, and A is harmonic quadrilateral, right?
You're saying we would want that to show that GI and A are collinear, right?
Yeah. So
Yeah.
HJ is perpendicular to AJ, right?
Yes.
And AJ is perpendicular to AO.
Yes.
Yeah. So therefore, HA, HO, HA, and HA prime is harmonic, right?
Sorry. So we want to show AJ, AH, AO. What are the four?
No. HA, HA, HO, and HA prime.
Okay. So because they're all perpendicular to another harmonic.
No. Because HA is parallel to AA prime, and HO is the median.
Oh, okay. So HO is the median in this triangle, and
Yeah,
HJ is parallel.
Yeah.
So yeah, that makes sense.
Yeah, so HA, HO, HA, and HA prime will be harmonic. And if we project on the circle, we will imply that J, I, H, and A is
harmonic.
Yeah.
And
Therefore,
so these are collinear.
Yeah, they must collinear, and we solve the problem.
Okay. Let me check the chat. Let's see what did Khan say. The circle with G is orthogonal. How do we know? So I'm reading what Khan said. How do we know that circle is orthogonal to O?
Well, because H lies on the polar of D, so that's how we define polar. Yeah. If a point lies on another point polar, then the circle with the diameter connecting those 2 points must be orthogonal to the circumcircle.
So the circle with diameter DH is orthogonal to O, but how do we know that G is the center of that circle?
We prove what we did.
We prove what?
We proved that. He proved that G is the midpoint of DH.
That G is the midpoint of DH.
Yeah, we already proved it.
Okay, like based on what Dat just said, or a different way?
Yeah, based on what we said. I think it wasn't that. It was really right.
Okay. All right. So yeah, we still have to use one harmonic. We just want to use it twice, basically. All right. So I'm going to start writing this up. So let the circle AE. Okay, so first let EF meet OD at G. And then let the circle AEHF meet AD at point J. Well, we'll say let it meet AD and ABC at I and J. Is that right? Or J and I. And then so first AEHF we wanted to show is harmonic, and that was true because ABTC is harmonic. So basically, so we said AT is a symmedian. So we start out with that fact. AT is a symmedian of ABC. So that means that ABTC is harmonic. Then projecting onto AEHF, let me make this a circle. What am I doing? Oh, there we go. And we have AEHF is harmonic. And so that means that well, so yeah, well, first we want to know GJ is tangent. Sorry, was that just like an angle chase, or yeah, how did we know GJ was tangent? I think Dan, you mentioned it.
Because I AG AG no GEHF is a harmonic quadrilateral, and you let EF cut the tension at H at G, so GJ will be the tangent as well.
Okay, that's right. So so we have AEHF is harmonic, and then we projected through H. So I'll say like
I think you mistyped there. It is supposed to be JEHF. JEHF is harmonic, not AEHF.
oh yeah, you're right. J. That's true. JEHF. So then since JEHF is harmonic, GJ is tangent. Okay, so really, yeah. So tangent to that circle. Okay, and then once we know that, we have HA, HO, HA prime, and HJ are harmonic. So HA, HA prime, HO, and HJ are harmonic. So I'll say let A prime be a diameter of ABC. And so projecting, well, yeah, so HJ, so I'll write that HJ is perpendicular to AB, means that HJ is parallel to A prime. A prime. And then we could take that, project it onto the circle. And then we would get HJ, AJIH is harmonic. So then A, I, and G are collinear. And then how do we finish off the problem? So then we know that GJ is equal to GH, and we're saying by an angle chase, we can show that that's equal to GD. So G would be the midpoint of HD, right?
Wait, did we need G is the midpoint? Because I used G is the midpoint to prove that A, I, and G is collinear. But I don't know if we did the same thing.
Yeah, that's the thing. I don't know if we proved yet that G is the midpoint.
If you already proved that G, I, and A is collinear, you don't really need it is the midpoint though.
Okay, so once you prove that these are collinear, you don't need to use that it's the midpoint.
Yeah, because GH square equal to because G lies on the radical axis, so GH square is equal to GR times GS.
Mm-hmm.
Yeah, so that means HRS is just tangent to.
Okay, because then GH squared is GJ squared, which is GR times GS. And so that proves the tangency. Okay. All right. So that means that GRH is similar to GHS. And so that implies that the circle HRS is tangent to GH, which is the same as OD. I like it. All right. Line as OD. All right. Yeah, that's a nice way to finish it. I like that. All right. So I'm going to move on to the next problem. But yeah, I think there was another way to do it. Yeah, maybe one of these harmonics, we could use poles and polars instead, like Khan said. Yeah, it's a nice solution. All right, so here's the next problem. This also looks like maybe an easier one. So we have a triangle ABC with circumcenter O, and we draw the tangents at B and C. So yeah, for that last problem, we used that AP was a symmedian. So I remember that from a previous video, but yeah, if you're watching on this channel and you haven't seen that before, try to prove it on your own. So the tangents intersect at T. So yeah, AT is a symmedian. And a line passes through T, and okay, we want to see where it cuts AB and CA. So it cuts AB at D, and then it cuts CA at E. Let me make this a little better. All right, so that will be point E right there. M is the midpoint of DE. And MA cuts the circle at K. And we want to show that the circumcircle of MKT is tangent to O, and it would have to be tangent at K. This is interesting. All right. Let's just check that. So the circle MKT. Yep, looks like it's tangent. Looks a little familiar. Yeah. So yeah, it's interesting how this can be like any line. Yeah, since M is the midpoint, it makes me think of like harmonics. So yeah, maybe it's worth dropping a perpendicular from B to AC. Are DF and K collinear? That would be very surprising to me. No, they're not. Yeah, they never use O. They never use the point O in the problem, but I'm going to draw it anyways. Looks like a fun problem. Draw a parallel through A to ET to get a harmonic bundle. Let's try that.
Oh yeah, just do that and yeah, we finish the problem.
Oh really? That was fast.
Yeah, really. So as he said, that is a harmonic bundle. So when you project it onto the circle, you will have a harmonic quadrilateral. So let's just call that intersection. Yeah, then we have K, F, and T is collinear.
Okay.
So a homotopy with center K sends A to M, F to T. So the circumcircle of KF is tangent to T.
Yeah, that's very fast. All right. So draw the parallel through A to ET and let it intersect the circle at F. F. And then AE, AM, AD, AF is harmonic. So yeah, then we can project and then so projecting through A onto the circle. We have that KBFC is harmonic. And that means that KF and T are collinear. And so then a homothety at about K takes the triangle KAT to KAF to KMT. So that means the circumcircle of MKT is tangent to the circumcircle O. Or I'll write it this way. I'll just say the circle MKT is tangent to KAF, which is the same as the circle O. All right. So we're getting through these pretty quick, and then there's those two harder problems. So this, I think, like the last of the easier problems.